Shall we start? Yes, Atharva.
Yes, sir.
Yes, sir.
Okay. So before we'll start continuation with the stress analysis, do you have any questions or doubts? Yes, Aditya Singh.
No, sir,
Gurpreet.
no doubt.
Okay. Ayush Patel. Atharva.
No, sir.
Okay, fine. Then Ravi. Prajakta.
No, sir, no doubts.
Okay, fine. Aditi.
No, sir, no doubt.
Very good. Shreyash.
No doubt, sir.
Shreyash. Okay, fine. Then we'll continue. Whatever we are discussed. Stress analysis. So is it visible to everyone?
Yes,
Yes. Okay, fine. Effect of sustained loads on fatigue strength. In earlier lecture, we had discussed about the expansion stress range, allowable stress range, and time-dependent stress, time-independent stress, and allowable stresses. As per ASME B31.1 and ASME B31.3. As per these two standards, we have discussed the time-independent stresses and time-dependent stresses. And now we will discuss the effect of sustained loads on fatigue strength. So might be you are familiar with terms that is fatigue in metallurgy or machine drawings. Now, here we'll see if the alternating stress is plotted against the cycle to failure. It can be seen that mean stress has an effect on the endurance strength of the material. What is endurance strength? Do you know anyone? Yes. Oh, correct. See, whenever we are consider the endurance limit, it is also called as a fatigue limit. Is the stress level below which an infinite number of loading cycles can be applied to a material without causing fatigue failure. Okay, it's called the endurance limit or fatigue strength. As the mean stress increases, the maximum possible permissible absolute stress, that is SA plus SM. So here allowable stress plus allowable mean stress. So increases while the permissible alternating stress decreases. The relation between the allowable alternative stress and the average stress follows the Soderberg's lines. Might be you have studied the Soderberg's equation in machine design, and which correlates fairly well with the test data of ductile materials. And the equation for the Soderberg's line is SA, that is stress, and to consider the respective equations, that is for r equals to 1. So here SA multiply 1 minus S of M or S of yield stress. So here R is nothing but S minimum or S maximum, minimum stress and maximum stresses. Now next is allowable stresses, that is maximum minus mean over 2, and mean stress equals to maximum stress plus minimum stress over 2 during the development of the ASME code section 3rd for nuclear piping analysis. The special committee to review the code stress basis concluded that the required adjustment to a strain control fatigue data curve based on zero mean stress occur only for the number of cycles in the range, that is 50,000 to 1 lakh for carbon steels and low alloy steels, and are insignificant to austenitic stainless steel and nickel chromium iron alloy. Since most of the plant piping come under this material of construction and the cycles of operation comes much fewer than 50,000 cycles in the life of the plant. The effect of mean stress on fatigue lives are negligible for piping material with ultimate tensile stress below 1 lakh psi. For high strength bolting material, where ultimate tensile stress is greater than 1 lakh psi, the mean stress can have considerable effect on the fatigue strength, and it should be considered when performing fatigue analysis. For piping analysis, the effect of solder line on the fatigue allowable is implemented in a conservative matter as per the code ASME B 31.1 and ASME B 31.3 covers it up in these different manners. So here we can see when the basic allowable stress at maximum expected metal temperature is greater than the sum of the longitudinal stresses due to pressure, weight, and other sustained loading. Sustained loading we called SL. The difference between them may be added to the term 0.25 into metal temperature stress, that is SH. This equation of allowable stress. So in that case, the allowable stress range will be to consider their different range per the allowable stress. In earlier slide, we have considered the particular range, that is f of f into 1.25 in bracket SC plus SH bracket close minus SL. As per the code, ASME B 31.1 covers these aspects in clause 102.32c. The difference between ASME B 31.3 and B 31.1 is that the stress reduction factor is indicated in tabular forms, and it covers up to 20 lakh cycles during the span of the system. So this value indicates different cycles and the factor remain the same in both cases. Now let us consider a typical example for calculation of SA, that is allowable stress. So here pipe supplies down thence to the impend of a reactor, which is operated on a batch process with a 4-hour cycle every 24 hours. The dothan system's temperature is 350 centigrades, and in Fahrenheit that is 600 centigrade Fahrenheit, and the material is ASTM A 106 grade B, design life plan considered 20 years. So the examples we have to calculate the allowable stresses. Now here we have to first step is to consider allowable stress at ambient. So that is 20,000 psi, and allowable stress at maximum metal temperature, that is SH, 17,300 psi. Now we have to calculate the number of cycles. Number of cycles means we have to consider the every 24 hours divided by particular hours. Here is 4 hours is given into total number of days in year 365 and plant design for 20 years. Therefore, we are to consider 24 divided by 4 into 365 multiply by 20. If you calculate here, 4 the 5 20, so here it will get the 20, and 24 into 365 into 5. So after multiplication, so we'll get 43,800 total. This is the number of cycles. Is it correct? 43,800 number of cycles. Yes, anyone? Check this calculation.
Yes, sir, it's correct.
Okay. Now next step. Here, stress range reduction factor is not given. As per earlier table, we have to consider the stress range reduction factor, that is 0.7. And to find out the SA, F into in bracket 1.25 into S of C plus 0.25 S of H. So here, allowable stress at maximum at ambient temperature, SE equals to 20,000 psi, and allowable stress at maximum metal temperature, SH, equals to 17,300. Here 1.25, here stress range reduction factor is 0.7, and then 1.25 into allowable stress at ambient, that is S of C is 20,000 plus 0.25 300, and calculate here S of A will get 20,527 psi. If you convert to kg per centimeter square, so here you will get 1,443. Is it correct? Calculate and verify your answers. Yes, it is correct.
Yes, sir, it's correct.
Okay. Now, see the limiting values of terminal forces and moments. and then centrifugal pumps. So, in limiting values of terminal forces and moments, that is, it has been indicated earlier that in case of strain sensitive equipment, the main consideration for flexibility are the forces and moments which a pipe impose on the equipment to which it is connected. The maximum permitted values of forces and moments will vary with the type of equipments. These are established by the regulatory codes based on which equipment is designed or manufactured. Or else, the manufacturers of the equipment set these values to ensure equipments for safe operations of the. Then we have to consider the regulatory codes referred by the piping engineers for different components like centrifugal pumps. In centrifugal pumps, we have to consider API 610 or ISO 5199. And second one is positive displacement pumps. That is API 676. Centrifugal compressor API 617. Reciprocating compressors API 618. Steam turbine, that is NEMASM 23, means National Electric Manufacturing Associations, SM23. And next component is air cooled heat exchangers, that is API 661 or ISO 13706. These are the regulatory codes referred by the piping engineers when we have to consider the limiting values of terminal forces and moments. And to consider next component, that is a flat bottom welded storage tanks, as per API 650, and fire heaters as per the manufacturer specifications. For the other statics equipment such as reactors, vessels, and tanks, interaction with the fabrication engineers is required to establish that the local stress developed due to nozzle loading are within acceptable limits. However, the values given under the ASME code B31.3 in section 3.10. Now, centrifugal pumps. The forces and moments are acting on the pump flanges. See here in centrifugal pumps, forces and moments acting on the pump's flanges. See here, direction is given X, Y, Z, discharge as well as suction loads. Therefore, pipe loads can cause misalignments of the pump and driver shaft, deformation and overstressing of the pump casings, or overstressing of fixing bolts between the pump and the base plates. As per the American Petroleum Institute standards, that is API 610, covering centrifugal pumps for general refinery service, is the one we specify these limits for pumps. The code specifies the criteria for piping design in regulatory codes. The allowable external nozzle forces and moments are given in ASME 31.3 and ASME 31.1 section 3. For nozzle size from 2-inch NB, that is nominal bore, to 16-inch NB. For pump with casing constructed out of steel or alloy steels. and then to consider kind of movements and force, and then orientation of the nozzle loads in terms of X, Y, and Z. API 610 specifies that the pump casing should be designed to withstand double the forces and moments as consideration. The piping configuration that produce loads and moment outside the different range is also acceptable. It is provided the conditions that is specified in the ASME B31.3. And for direction of forces and moments, here you can see the diagrams for direction and forces, the moments. Then we have to consider their respective directions as well as discharge and sections. For the orientation X, Y, and Z. So here we can see the nozzle orientation of nozzle loads. Now, horizontal pumps with top section, top discharge, and horizontal pump with end section and top discharge. As per ISO 5199 to 2002 gives the allowable value of forces and moments on the pump nozzles. The basic values given the ASME code 31.3 and corresponding coefficients are also given. This is based on the study and test undertaken within European Association of Pump Manufacturers together with the support of piping specialists. Then we have to consider their values. Now next is positive displacement pumps. The American Petroleum Institute standards, that is API 67, specifies in class 2.4 the limiting values for the rotary positive displacement pumps with alloy steel or steel casing at inlet and outlets. To consider their forces and moment values and to consider their appropriate nominal diameter of the nozzles in inches. So as concerned the positive displacement pumps. Now next is centrifugal compressors. Then American Petroleum Institute as per API 617 centrifugal compressor for general refinery services has been specifying that the compressor shall be designed to withstand external forces and movement on each nozzle at least 1.85 times the value calculated in accordance with the NEMA SMs, that is National Electric Manufacturer Associations. So here, for the experience, the piping engineers, there has not been uniform interpretation of 1.85 times the NEMA. Therefore, API 617 has modified the equation and is attached in ASME 31.3 for formulae for the calculation of the acceptable forces and moments. The forces and moments acting on compressor due to the inlet pipe and discharge pipe connections. Kind of forces and moments are acting due to the inlet pipe and discharge pipe connection. That is, first one is resultant force and total resultant moments imposed on the compressor at any connection must not exceed the 3F plus M less than equal to 9 927D or F less than equal to 927D minus M over 3 and F plus 1.09M less than, that is 5.41D in SI units, where F is resultant force, M is resultant moment, and D is pipe size of the connections in IPS or in inches per millimeter up to 8 inch and diameter in 200 millimeters. For size greater than this, using the value of D equal to 60.60 plus IPS over 3 inches or 400D over 3 in millimeters. Now next criteria for consideration, the combined resultant of the force and moments of the inlet and the discharge connection resolved at the center line of the discharge connection, or this is called the largest connection, must not exceed Fc equals to 462 dc minus mc or 2 in USCS. That is, USCS is nothing but US customary system, and Fc can considered in SI units, that is 40.4 dc minus 1.64 m of c in SI units. Here Fc is a combined resultant of inlet side and discharge forces in pounds per Newton. M of C is combined resultant of inlet side and discharge moments resulting from forces in foot lbs per Newton meters. Now, here we have to calculate, that is a DC, the equivalent diameters to consider for this process in inches and millimeters. Then to consider their components of this resultant in US customary units and in MKS units, forces and moments, that is F of Y. So force acting along the Y direction, Z direction, and X directions, and moments acting along the X, Y, and Z directions. And here their respective values are given. For the forces, we have to consider the force acting on the Y directions, that is 231 of DC, and F of Z 185 DC, F of X 92 DC, and respective moments of X axis, that is 462 of DC, and M of Y is 231 of DC, and M of Z equal 231 DC. And in MKS units, values are given F of X, F of Y, and F of Z, forces acting along the X direction, Y direction, and Z direction. And likewise, moments for X direction, Y direction, and Z direction in MKS units. Here, F of Y is a vertical component of Fc, and F of Z is horizontal component of Fc. See, here might be seen the forces. F of Y, the vertical component of Fc, and F of Z is horizontal component of F of C. And F of X, horizontal component of Fc parallel to the compressor shafts. And to consider their values for moments for m of x component of Fc in a horizontal plane parallel to the compressor shafts, and m of y is component of Fc in vertical plane and moment for z component of c in horizontal plane at right angle to the compressor shafts. So to consider these components of this resultant shall not exceed, considering these values as per ASME code 31.3, and we have to consider the plan and elevation compressor shaft. So here to consider the discharge and sections, the plan, the compressors, and then elevations, the compressors, and end view, these compressors. So here you can see all three views, these compressors. Based on this, we have to consider their respective values are acting on different directions, x direction, y direction, and z directions. These values of allowable forces and moments pertain to the compressor structure only. They do not pertain to the forces and moments in the connecting pipings flanges and flange bolting, which should not exceed the allowable stress as defined by applicable codes and regulatory bodies. Forces on inlet connection are to be transferred along with the moment to discharge connection to analyze the compressor for resultant forces and moments. But the transfer of forces will generate additional transfer moments, which are added to the total of moments to give resultant moments. So that's concerned the centrifugal compressors. Now see the reciprocating compressors. As per API, that is American Petroleum Institute 618, reciprocating compressor for general refinery service do not specify the limit on the allowable forces and moments in the code. The vendor shall specify the forces and moments for each nozzle in different tabular forms. However, the values as per API 610 can be considered for guidance. So that's concerned the reciprocating compressors. Now next is steam turbine. As per NEMA SM23 requires, NEMA SAM requires that the forces and moments acting on the turbines due to the steam inlets, extraction, exhaust connection should be evaluated by simple set of forces or moments calculation similar to centrifugal compressors. This computation we can discuss like the total resultant force and the total resultant moment imposed on the turbine at any connection should not exceed the values as per this equation, that is 3f plus m less than 500d or f less than 500d minus m or 3. Here F is resultant force, including pressure force, where unrestrained expansion joints are used at the connection except on vertical exhaust. Full vacuum load is allowed on vertical down exhaust flanges. Then, to consider equation, that is resultant force equals to under root of f of x square plus f of y square plus f of z squares. Now, resultant moment, that is under root of mx square plus my square plus mz square. And to consider diameters, so that's concerned, the diameters, that is nominal pipe size, the connection in inches. So up to 8 inch for size greater than, and we can use diameter equals to 16 plus IPS in inches or 3. And then we have to consider the combined resultant of the forces and moments of the inlet, extraction, and exhaust connection resolved at the center line of the exhaust connection should not exceed F of C equals to 250 dc minus mc over 2, here where F of C is a combined resultant of inlet, extraction, and exhaust forces in LBS. And MUPC is combined resultant of inlet, extraction, and exhaust movements, and movements resulting from forces in foot LBS. Now DC is diameter of circular opening equal to the total areas, the inlet, extraction, and exhaust opening up to 9 inches in diameters. To consider this much value for diameter of a circular opening equal to the total area of the inlets, extraction, and exhaust openings. Now, values beyond this, then we can use the value of DEC, that is 18 plus equivalent diameter in inches over 3. Then we have to consider the component of this resultant should not exceed f of x equals to 50 dc, f of y equals to 125 dc, and f of z equals to 100 dc. That's concerned the moments for x 250 dc and m of y equals to 125 dc, and moment for z equals to 125 dc. And here, what is f of x? Horizontal component of f of c parallel to the turbine shafts. Earlier we are considered the compressor shafts. Now f of y is a vertical component of f of c, and f of z is horizontal component of f of c at right angle to the turbine shafts. And as far as concerned the moments, that is m of x, m of y, and m of z, that is component of m of c around the horizontal axis parallel to the turbine shafts, and m of y component of m of c around the vertical axis, and m of z component of m of c around the horizontal axis at right angle to the turbine shafts. For installation, the turbines with a vertical exhaust and uncertain or unrestrained expansion joint at the exhaust. An additional amount of force caused by pressure loading is allowed. This additional force is perpendicular to the face of the exhaust flange and is deemed to act at its centers. For this type of application, calculate the vertical force components on the exhaust connection, excluding pressure loadings, and compare this with 1/6 of the pressure loading on the exhaust. Use the larger of these two numbers of the vertical forces component on the exhaust connections. So making this calculation for these equations, the force caused by the pressure loading on the exhaust is allowed to in addition to the values established by the foregoing up to a maximum value of a vertical force in pounds on the exhaust connections, as including the pressure loadings, that is 15 times the exhaust area in square inches. These values of allowable forces and moments pertain to the turbine structure only. They do not pertain to the force and moments in the connecting pipings, flange and flange bolting, we should not exceed the allowable stress as defined applicable codes and explanatory notes in ASME B31.3. Therefore, to consider the respective component forces and moments on turbine connections. So, this is all about the steam turbines. So, see, any doubts or any questions from your side? Yes. Ravi, Praful, Prajakta.
No, sir. No doubts.
Okay. Pratik.
No, sir.
Okay. Ash. Aditi.
No, sir.
Okay. Aditi. Okay, fine. Then we'll close this session here and we'll continue in next.
So, can
Yes,
you
Siddesh.
tell us the name of the book which you are referring? Means because for the MST means we want a reference book.
See,
So
all
in
book.
piping handbook means is there everything available? Like there are some parts which are like felt a bit confusing.
See, there is no need to confuse, Siddesh. Whatever material uploaded in Google Classroom, you go through this. There is no need to refer any extra books. If you want to refer extra books, so in syllabus, in a first slide, so textbooks and reference books are mentioned. The first slide is piping engineering.
Yeah. Yes, sir. Yes, sir.
So you can refer any books. If you refer the whatever uploaded materials in Google Classroom, that is more than enough for piping engineering.
Yes, sir. Okay. Thank you, sir.
Okay, fine. Any doubts? Anyone? Any questions regarding textbooks, syllabus, question pattern? But don't ask what kind of question will appear in exam. Yes. Aditya Singh, do you have any doubts, question?
No, sir. No doubts.
Okay, fine. Then we'll close here and we'll continue in next lecture.